Here we're going to look at graphs of position, velocity, and acceleration for an object in simple harmonic motion attached to a spring. And the graphs that we're going to make are going to start at t equals 0, where the object has a velocity in the upwards direction already. And it has that upwards velocity because maybe I attach that object to the spring. It comes to rest at that equilibrium position, which is that dotted line, and then I pull the object below that equilibrium position and I let go. And now that object is rising upwards and currently is at t equals 0 at the equilibrium position with a positive velocity. And then our graphs are going to cycle through one full cycle of the object's motion until t equals capital letter T, when that first full period, first full cycle of the object's motion is completed. For starters, we're going to look at the position versus time graph, where if we define the equilibrium position to be the place where y equals 0, then positions above the equilibrium position are positive and positions below that are negative. And so at t equals 0, the object is moving up, but it is at equilibrium, and so its position graph should start off at y equals 0. And since the object is going to be moving in the positive direction, I know that my graph needs to be moving in the positive direction as well. At t equals 1/4 of the period, the object is at its maximum compression. It's at the distance furthest away from equilibrium. It's at its maximum displacement, which is its positive amplitude, which I can indicate on the graph in that way. After 1/2 of the period has elapsed, the object returns back to equilibrium, and so its position is once again 0. After 3/4 of the period, the object is an equal distance away from the equilibrium line as it was at 1/4 the period, but now that amplitude is below the equilibrium position, and so it's a negative amplitude. And then finally, after the entire period has elapsed, the object returns back to its original position at y equals 0. And so you can see from these dots that the graph looks kind of like a sine curve where it cycles through its positive and negative amplitudes, oscillating between equilibrium, positive A, equilibrium, and negative A. Next, I'd like to look at the graph of the velocity of this object as a function of time. And when I look at t equals 0, I see that the velocity of the object is positive because it's moving upwards. I also know that if I were to look at the position where 1/4 of the period has elapsed, which is here, or the position where 3/4 of the period has elapsed, which is here, then at those positions, the object needs to momentarily stop and then change direction. So at 1/4 the period, right before we got there, it was moving up, and then right after we got there, it's moving down. And so it stops and changes direction at that moment and at 3/4 the period. And so for that reason, at those locations, we will have the biggest net force acting on the object, the largest acceleration, but the smallest speed, because as it reaches and then leaves those locations, the object is going to be slowing down and then speeding up in the other direction. So the speeds will be the smallest. In fact, they'll be 0 at those locations with the green dots. And at the locations where the object is at equilibrium, the speed will be a maximum, and the velocity might be positive or negative depending on which way the object is going. So for starters, at t equals 0, the velocity is a maximum value because it's at the equilibrium position, and it's positive because initially the object was pointed upwards. And so my velocity is going to be some positive value that'll be the maximum positive velocity that it has. And at 1/4 the period, the object is going to stop and turn around when it reaches that maximum positive displacement, and so its velocity will be 0. At 1/2 t, the object is back at equilibrium, but this time the velocity will be in the negative y direction, so its velocity should be negative. So it's some value negative v. And notice how at t equals 1/4 t, the velocity of this object has passed through the time axis on this graph, which indicates a change in the direction of the object, right? At 3/4 of the period, the object is once again going to momentarily stop and then change direction. And so we should see that change in direction in our velocity versus time graph as the object is passing across the time axis. And then at t equals t, when the object is returned to equilibrium, in my picture up above, the velocity is now once again in the positive y direction. And so the velocity in my graph should be that same positive value as it was initially. And now slightly differently, when we think about the acceleration versus time of the object, we know that the acceleration is proportional to the net force that is being exerted on this object. When I attach the mass to the spring and it just comes to rest at that new equilibrium position, the reason why that's the equilibrium position is because if I haven't pulled it down and set it into its motion yet, then the forces that are acting on that object are equal. So the upwards spring force and the downward gravitational force, those two forces are equal, which means the object is at rest. But then if I displace the object by pulling it down and letting it go, then of course those forces change and then cause the oscillatory motion of the mass. At the maximum positive displacement that we see at 1/4 the period, the forces are no longer going to cancel each other out. And the reason is the gravitational force still points downward, so that's mg, but the spring force is now also going to point downward because the spring has been compressed, and so the spring wants to be restored back to its length at equilibrium, and so the spring will push down on the mass in the same direction as the gravitational force. So those forces no longer cancel with one another, they actually add together and produce a large downward net force. So when I make my graph of the acceleration versus time, initially the object is at equilibrium, and so the acceleration, we should expect that that's 0 because the net force on the object is 0. At 1/4 the period, the acceleration is its maximum value because the net force is as large as it's going to be, and that net force points in the negative y direction. And so if the net force points in the negative y direction, the object's acceleration will also point in the negative y direction. And so in my acceleration versus time graph, I need to make sure that that acceleration is negative, some value minus a. As the object comes back up to equilibrium, the forces will equate once again, they'll be equal, and so the acceleration will go from being negative back to being 0. And then as the object comes back to its maximum negative amplitude, once again the acceleration will be its largest value because the net force on the object is its largest value. Here the gravitational force will point down, but there will be a much larger upwards spring force acting on the object because now the spring has been extended by much more than what it was at its equilibrium length. And so here the acceleration will be in the direction of the net force, which is in the positive direction, so the acceleration is positive. And then lastly, when the object returns back to equilibrium, once again the net force will be 0 and the acceleration will drop off back to 0. If we were to continue making these graphs, what would they look like? Well, if we are pretending to have a system where frictional losses are negligible, where there's little to no friction lost, then these graphs would continue on forever, right? With the same amplitudes, with the same sort of frequency of up and down motion, which would match the motion of the object's simple harmonic motion. But for most real systems, whether it's a pendulum or a mass spring system, we know that while it might oscillate up and down or back and forth for quite a while, eventually the motion seems to dampen out. And that's exactly the word that we'll use to describe what's happening. So the damping of most real systems is something that we have to consider. And if we were to make graphs of any of these quantities, so whether it's the position, the velocity, or the acceleration, while I don't know where to start this graph, I'll just say that if I make graphs of any of those quantities, if they start off with some amplitude that looks like this, over time that amplitude will slowly decrease as the energy is being removed from the system by those resistive forces, whether it be some friction in the spring or the air resistance from the mass moving up and down. Energy is being removed, and so we'll see the amplitudes of these graphs shrink, and they'll shrink down to nothing. And so that physical thing that's happening there is the damping of the energy of the system. We only looked at a few different graphs here, but there are other graphs that could be asked of you as well. For example, the kinetic energy versus time, or perhaps the potential energy versus time, whether it be the elastic potential energy, the gravitational potential energy, or both. The net force versus time, or something else entirely. Right? And some of those graphs might look incredibly similar to one or more of these graphs that I've drawn, but some of them might look a little bit different. Lastly, I'd like to just caution you and say that since all these graphs look quite similar, it's very easy to mix them up, to get them backwards, or to start in the wrong spot. And so I'll leave you with a little bit of advice. I'd like to just say that one of the things that students miss the most is where to start some of the graphs. And so I'd like you to always ask yourself, at t equals 0, where is the object? Incredibly important to ask yourself that question. Right here, the object was starting off at equilibrium, so I knew to make my position graph start at y equals 0. And then all of the graphs follow from that. Another question that's important is at t equals 0, in what direction is the object moving? If you don't know what direction it's moving to begin with, then you can't start moving your line on any of these graphs in the positive or negative direction. So it's critical that we know not only where does it start, but in which direction is it moving when we start making our graphs. Lastly, you're not always going to start at t equals 0 with the position. Sometimes you might be given the acceleration versus time graph or the velocity versus time graph, and from that graph alone be asked to make the other two graphs. And so we need to make sure that we not only understand how to take one of these graphs and match it up to the picture, but how to take these graphs and match them up with one another. And so in order to make that as easy to understand as possible, I'll just point out a couple relationships. I know that the object moves fastest at equilibrium. So everywhere in my position versus time graph where I see that the object is at equilibrium, I better have a velocity, or a speed at least, that is a maximum value, whether it be positive or negative, and that's what we see. I also know that the acceleration is going to be the biggest when the object is at its maximum displacement from equilibrium. So at maximum displacement, here and here, I'm seeing the maximum acceleration, whether it be negative or positive. And so those are the kinds of relationships that you should be looking for, and those are the types of things that will really help if you're asked to use one graph to produce the other two. And so right now I would highly suggest that maybe you switch this out with a pendulum, and maybe you, instead of starting off at equilibrium, you start off with the object at its maximum amplitude, whether it be moving to the left or to the right. And given that picture, given that scenario and those restrictions, try to go ahead and make all three of these graphs and see if that's something that you feel comfortable doing or not.